So the final speaker of this afternoon's session is Anna Lundin. Anna is the technical lead at RAYSEARCH Laboratories, where she works with advanced software innovations in the fight against cancer and to help hospitals design radiation therapy treatments. As a domain expert and technical lead, Anna's goal is to build a logical, fast, and easy-to-use application based on solid, safe, and extendable architecture. So please welcome Anna to the stage.
Hi, glad to be here. The final talk is going to be something that's completely not network. I'm going to talk about how to use software in the fight against cancer. I studied in Uppsala, Master of Science in Computer Science. I worked last 20 years with computer software development in medicine. First, we're writing an API for haptics and graphics interaction. Haptics is where you can touch things with the force. And then we utilized that API to write medical simulators. It was a great technique. It was quite the opposite of the management. So then I transferred over to RAYSEARCH, where I work today. We work with software for planning cancer treatments. I started with deformable modeling, very similar to what we did there, but to be able to track the dose in patients when you move over time. Then I've been technical lead for our major software product for a lot of years, and now I also work a lot with product owner questions and try to get new cool stuff into the model in a consistent way. So RAYSEARCH, when I started, we were around 20 people. We worked in Unix environment, wrote C++ in Emacs. We had a plugin that only did optimization services to other vendors. They didn't want to be as fast as we wanted with getting out new cool stuff there, so we started to sell to end users. That means that we have grown very much. We didn't have one sales guy and no support. Now we have much more of that, so we're 292 employees. 146 in research and development, and all of us sit in Stockholm. There we also have the management and more of that. We sell to clinics all over the world, so we have a lot of subsidiaries and also distributors. But going over to what I'm going to talk about is how you use software for planning radiotherapy treatments, and also a bit about why you need very advanced software to plan for radiotherapy. To start, we work with external radiation, and that is that you direct the radiation at the tumor from somewhere outside of the body instead of inside. What you see here is a linear accelerator. That's the most common one. Many thousands of those exist out there, and they use photons, X-rays, or electron beams to aim at the patient tumor. The aim is to destroy the cancer cells and then spare as much as possible of the surrounding tissue. You can also use the same if you just want to relieve pain, if it has gone too far. Going back here, this arm here can turn around. And in the upper part here, there is something called a multi-leaf collimator. Or now it is. It could also be as a square or a round shape. But in the recent years, it offers a leaf things where you can move the leaves in the upper part, and then you can shape the beam down towards the tumor to get a much more consistent delivered dose. When you do treatment planning, our aim is to create a specification that the machine will then use to deliver that plan to the patient. So we more or less create a plan, and we use a standardized protocol called DICOM, like Digital Imaging and Communications in Medicine, where the specification will be delivered. So our job is to create the best specification possible for each individual patient. So this is our software called RAYSTATION. And as you can see, you can look at the machine down to the left. You can see the dose. You can see where the beam comes in at different directions. One important thing is that when you create a plan, you need to create a specific plan for each individual person. So you need to know the position of the tumor, you need to know the size and the shape, you need to know how aggressive the tumor is, and then the density and shape of all surrounding tissue. So if we start, we have a patient. This is a lung patient. You can see the tumor up here. Back off. So you have to aim the beam in the middle of the target, and then you can shape all the leaves around the target with the multi-leaf collimator. And then you can deliver the dose. You believe. But if you start off, you're going to see that down here is the tumor. The beam comes in front of the patient, and you see here, the red part, that's the high dose area. So we get a lot of dose to the patient that kills parts, but not where the tumor actually is. And that is due to, if you look at the depth of photons, it is like it enters the body. It's, no, wrong button. Me too. Photons, when they have high speed, they deliver a lot of dose. When the speed decreases, it doesn't deliver as much dose any longer. So you can see that when we enter the body, it's a lot of high dose, and then it just shrinks. So we need to do something. This is the patient. I'm going to show this again so just so you know where you are. Here you see in the view of the beam. Down here you can see that the beam is entering from the front. Here you see the front. And then I'm going to click once more. Now you see the beam in front in here. And this is actually a slice of the patient. So you can see that the beam is entering up here. So what we have to do is to deliver a lot of beams from all around the body. So you get the high dose area in the middle of the tumor. Then comes the next problem. This is a water square, and we have 3 exactly equivalent beams coming in here. All of this is water except this part where it's air. Down here it's bone. And if we deliver just one beam here, we can see this high dose area here, and it reaches down here. If we deliver this beam and there is an air gap, the photons will not stop, be hindered, so they will continue to have the same high speed. High speed when they get out of the air. So you actually move where the high dose area is. If you instead hit something that has a higher density, all the beam's going to get stopped. This means that you need to know how all the surrounding tissue is, all around where the tumor is, to know what actually the delivered dose will be. And if we take a look at this again, you can see now this beam is entering down here. I don't know if you could, but see there's like green streaks down there where we actually have taken into account the actual density of the patient. So this means that you need to know a lot about the patient. There's a lot of different imaging techniques: CT, computer tomography, MR, or MRI it can also be called, ultrasound, PET. We always use CT, or almost often, when we plan for radiation, because it's very stable. You can go directly from a CT pixel value over to what the density actually is. You match that per CT machine, as we can see here to the right. This is just an image of a CT machine. It takes X-ray images from a lot of angles. It processes it with computer, and then you get a lot of slices out of this, one by one, that we can import into our software. What we do is that we build a full 3D volume out of this, that you can scroll through, look through, and see what happens. You can see in one slice or over the full body. And then you can define how the anatomy of the patient actually is. So by knowing the patient anatomy, we can compute the dose, and we can present what the dose will be to the patient. But when we have all this information, it has been historically a lot of hard work, human fiddling around with things. Then the idea came, what if we just tell the computer what we want, and the computer can create the optimal plan? You want a lot of dose in the target, and you want no dose outside of the target. And also it's a bit more intrigued than that, because here we have the target that we want like to have a lot of dose. If we have the spinal cord, it's like a nervous system. You need to have signals going from one end to the other. There we're very much interested in the maximum dose, because there will be no signal if something is dead in the middle. If we take a look at the lungs instead, we don't care about a little bit, because you can survive with the rest of it. So different areas in the body requires different, can cope with different amount of radiation. So what we do, I don't know if everyone sees it, but down here, we have just set up like equals objective function, which tells us what we want. We say that the lung tumor, that we would like to have a uniform dose. We say that in the rest of the body, we want it to slide down. In the spinal cord, we say that there is a maximum dose. And in the lungs, we say, oh, the medium dose are not allowed to exceed a certain extent. And then we go ahead and compute. And maybe you see up into the right here that for each time we compute, we move the leaves a little bit, we compute the dose, and we try to move them in the way that makes the most optimal dose out of this. So what will happen then is these leaves that were sitting up there to create a good shape, you can see them down here. So if I play here, you're going to see that for this beam, if it plays, no? It doesn't. Okay, no, it did. You're going to see that from every angle, it tries to find, it delivers several times from each place. So it can sculpt the dose. It says if I take a little bit there, and a little bit there, and a little bit there, it can shape the dose much more. And that means that if we take this case as an extreme case, you can deliver a lot of dose, and then you can sculpt out something that you actually would like to spare. And the cool thing about this is that most often you don't aim at a higher kill rate. What you strive for is try to protect as much as possible about the surrounding tissue, so that after you get the treatment, you actually get a good life afterwards. So that is often the biggest aim of what we do. So if you then presses this type of machine to the maximum, you can see that down here you can see that now we're delivering radiation, and you can see that the leaves are moving meanwhile we actually radiate. And if you take a look at the upper part, you can also see that the full machine is swiveling at the same time as you deliver dose. So in this way, we can actually sculpt the dose that we would like to deliver to the patient. Photon machines. The Linac that we talked about, there are a lot of different types of them. We support a multitude of them. We are not vendor dependent. We plan for a lot of the types and try to push each machine to its limit of how we can modulate that to achieve the best possible plan. Then if we go over to something that's proton therapy, maybe you've heard of. Protons are cool. If we look at this line here, it was the photons. They enter the body, and then they slow down, and then they deliver less and less dose. Protons, they are the opposite. The slower they move, the more irradiation they deliver. So when they enter the body, not that much dose delivered and they go slower and slower, and then they start to deliver a lot of dose until they put the end, delivers a lot, and then just stops. So you don't get an exit dose and hardly no entry dose. You can just deliver the radiation in the middle of the patient. To know why we don't all use this, we have to go back and watch our Linac. You can see here, this is the full radiation. This is the machine. This is what's needed for a hospital. Going over to the proton, this is what is needed. So here we have the patient. And over here we have a little linear accelerator that puts a lot of speed into the protons or carbons or other ions. And then they go into an accelerator that accelerates the ions to deliver them and bend them and get them into the gantry and off to the patient. I'm going to show you, this is and start off, we look at the accelerator, and then we're going to take a look at the gantry. So she's moving in here, and what you see here is the accelerator, and the red and yellow parts are magnets that focuses the beam. And this accelerator is a cyclotron. It takes the protons up to 3/4 of the speed of light. And then after that, this is 64 square meters in circumstance, and it weighs 600 tons. So this is the gantry. This is 600 tons. So what you can see here, what was the one that were rotating on the LINAC. This is what's rotating on the Proton machine. And that's the one that weighs 600 tons. And if we look at it, it rotates, and here it's actually around the full room. So the patient enters from the top and inside of the room, and then the gantry rotates around the full room. So it's money, I would say, is the cause. But it's very fun with Proton parts is that as Linux you can just buy off the shelf, more or less, whereas Proton clinics you often build very specific. So we're often part already from the beginning when they build this system to make sure that we know what dose will be delivered, that they have some special things to shape the dose in their specific way. So we need to add support for that. So often we're part of the development of a new Proton center, which is very fun. There isn't that many Proton centers in the world. There's 82. United States are the biggest, and Japan is a lot. There's 24 in Sweden, no, in Europe, and Germany has 8, which is the biggest. We have one in Sweden, the Scandian Clinic in Uppsala, and they do not have our planning software. Yet. Now, they want it, but there is like the upphandling, whatever that's called. And what you can see here is like we are very large on the Protons, but what you can see here is like these are clinical, but we also have a lot of customers that not clinical yet, because it's a long process of being able to write the software for this clinic. This is our software back again. Once upon a time, we had Unix, Emacs, C++ only. Yeah. Now we're Windows. We're very much Windows. We wanted a familiar system. A lot of the planning systems for radiotherapy was very old. So there were a big drive against having something that looks shiny, nice, modern. So we have a VPF user interface. It has high abilities to shape the user interface the way you want it. The application layer is in C++. In C#. So all the parts that you see and can move and so forth is C#. Then we have computational services, C++, that you call. And we have a lot of computations on GPU, where we recently have changed to CUDA. We had AMP before, so now we're NVIDIA only. CUDA had a lot of problems. We have the OpenGL graphics, full 3D rendering of everything. We have created a Python scripting interface that both we and our customers can use to directly reach our model. And the database is on Microsoft SQL Server. So we work in Visual Studio, mostly. We use MATLAB on the research department to evaluate new optimization strategies and so forth. Our full database, we don't call it the database, we call it the domain model. We have like, if you have worked in 3D graph, it's a scene graph. Everything is built with an owner that depends on the other, and we have a lot of invalidation rules, a lot of validations. So all our security resides in our actual domain, which means that we can allow the scripting interface and the user interface to edit things in as they want, because we know that we keep the security in there. This also is, we do this to code generate everything. So the mapping to the database is directly code generated. So we have full access to how everything is stored. We don't send and take, we only store and save. And we have checksums to validate that what we actually wrote to the database the last time is the same that we read the next time. Use Microsoft Team Foundation Server. Going to move over to Git now. 2 million lines of C#, 1 million lines of C++ into one gigantic application. So we have an inbuilt build tool to build all our different projects one by one. Tests. We have 28,000 unit tests, 8,000 integration tests. Dose validation tests, that's when we compute for each machine that the dose will be delivered. A lot. Some of them we run before every check-in, since we deliver to the same code. Some we run as fast as we can. We have 2 gigantic servers with graphics cards that just runs our tests all of the time. Finally, view from our office. I like this. I have 1 foot in the research, 1 foot in the industry and market. Always strive to take those research results and try to push it into the software. You can work with cool machines. Now we're adding machine learning in this new version. It's always new cool things to add. And I like that when you work with software engineering, you're like, I would like to do something cool, maybe project a missile or something. But here you can do it, but actually do something good for people. I like that. Thanks.
Do you have any questions for Anna? Okay. Please join me in thanking Anna very much for the presentation. Thank you. So that is the end of today's NetNut technical meeting. Thank you very much for coming. We're ending a little bit early, so it gives you all a good chance to just do one final check of your DNS resolvers, because time is ticking. The buses will leave for the social at 5:45 sharp, just outside of the hotel. But for now, we would just like to thank you very much for coming, and thanks to the sponsors, Arista, Conapto, and Baffin Bay Networks. And we hope to see you again. Thank you very much.